Now that you have an understanding of how recombination works, it's time to extend these ideas to looking at three loci at the same time. A test cross of a trihybrid is also known as a three-point test cross, and you'll see these in your textbook, and we'll work through an example here. So if we have these two pure lines as the parents, they each contribute a gamete to the F1. This one will contribute big A, little b, little c. This one will contribute little a, big B, big C. And the F1 will be a trihybrid that is like this. And I'll write it this way to show the extra information showing what the two input packets were. We could also write this in the standard form, but that would not give us as much information. We can now consider what gametes this F1 trihybrid can produce. Whereas before with a dihybrid we saw that there were 4 different types of gametes that could be produced. Now with the trihybrid we'll see that there are 8 different types. So we can see here that the trihybrid now can produce a number of different gamete types. As we mentioned before, a dihybrid will produce 4 different output products of meiosis, and a trihybrid, as you can see, will produce 8 different categories. Now, the linkage arrangement or not of these loci will not influence the types of gametes that are produced, only their relative frequencies to one another. If all 3 loci were unlinked on separate chromosomes, we would see that these gamete frequencies each would have a frequency of 1/8. It's often the case with a 3-point test cross that you're dealing with at least 2 loci in the same chromosome and often 3 loci all in the same chromosome, in which case these will not have equal frequencies. It will be dependent on crossing over. Now, the way to tackle this and ask whether or not a gamete is recombinant or not, the way to tackle this is to effectively ignore one of the loci, say now just between the A and B loci, score each of these as recombinant for A and B, then move on to say ignore the B locus, now score A and C, and then so on, then ignore A and score B and C. The way to keep organized when you're doing this is to make yourself a little chart. Let's score the A to B interval, the A to C interval, and the B to C interval. And here is where keeping these products of meiosis together in what I call cognate sets is a useful thing. The same meiosis that produces this big A, little b, little c at the same time will also produce little a, big B, big C. So it's useful to keep them together, and it speeds up the scoring, as you'll see in a moment. Okay, so for this product of meiosis here, we have a big A and a little b, and as you can see, that came in on one of the input sets. So we would score this as non-recombinant. Here we have a big A and a big B, and you can see that that combination of alleles was not present in either input gamete, so we would score this one as recombinant for A and B. Big A, little b, we saw that before, that's non-recombinant. Big A, big B, we just mentioned, is recombinant. Okay, then we can move on to A and C. Here we have a big A with a little c. You can see that that came in, so that's non-recombinant. Oops. You'll also notice that these two output products are exactly the same as the inputs, and it's often convenient to draw those ones up at the top because you can conveniently score them, all 3 of them, as non-recombinant for all 3 intervals. Now let's say A to C, big A with little c. We saw that before, so that is a non-recombinant. And we should just check little a with big C, yeah, that's not recombinant as well. Big A with big C, haven't seen that before, so that's recombinant. And little a with little c, again, that's recombinant. Big A with a big C, that's also recombinant as well. Another thing to point out to help you to make sure that you're on the right track, a way to check, is you should always have exactly 2 non-recombinants and 2 recombinants in any given column. So if you end up with 3 non-recombinants in one column and only 1 recombinant, then you've made a mistake somewhere. Okay, let's shift over to B to C. So here we have little b and little c. We saw that together, non-recombinant. Big B, little c. Haven't seen that before, so we'll score that as recombinant. And we'll just check here, little b with a big C, again, recombinant. Okay, little b with a big C, we just scored that as a recombinant. And big B with a little c, we score that as recombinant as well. Last one, big B with a big C, that was present in this one here, so this is a non-recombinant haploid genotype, and little b, little c came in from here. Another way to check that you've done this correctly is that none of these columns will have the same pattern of non-recombinant and recombinant. So here you see we alternate, and we group these two together, those two together, and here we have them in a different pattern. So if you ever have two columns that have exactly the same pattern, then you know that you've messed up something as well. Now, the way you take this from here is simply to look at the actual numbers of the different possible outputs. And then what I'll do now is I'll put some numbers on this, and then we'll come back and actually show how you go through and do the mapping. Okay, now we have some real numbers. Now, where these numbers would come from would be from whatever question is that you're attempting to solve. Now, one thing that I'm sort of skimming past here is you get these numbers by determining from the progeny of this trihybrid their phenotypes when they're crossed to a tester. So what we've done is taken this trihybrid and test crossed it to an organism that's only going to provide the recessives of all three loci. What this allows us to do is to determine what the haploid genotype of the output product of meiosis was for any given offspring in the F2. So here now we're talking about the F2. So for example, if we see something that has all three dominant alleles in the F2, so it doesn't have any of the recessive phenotypes, then we know that it received this particular gamete from the F1, and we can infer that because it's getting this gamete from the other parent. So the tester is not providing any alleles that alter the phenotype in any way. So what you have to do in a given question is you actually have to go through, look at the actual numbers, and match them up with a particular haploid output genotype that's coming from the F1 trihybrid. Once we have these numbers in place, then what we can do is we can determine recombination frequency for each of the intervals. So I just need a little bit more room here, so I'll just wipe that off. So let's do recombination frequency now for the A to B interval. Now, the recombination frequency is simply the total number of recombinants divided by the total number of products of meiosis for a given interval. So all we're going to do here is we're going to look through and say, okay, here are my recombinants for A and B. Here's some, and here's some. Out of a total, this will add up to 1,000. So the recombination frequency for A to B would be 34 plus 36 plus 6 plus 4, all that together, divided by 1,000. Okay. The recombination frequency from A to C again, the same thing, we just go down the column and say, okay, here are the recombinants. So it would be 62 plus 58 plus 6 plus 4 divided by 1,000. And then the recombination frequency from B to C will be simply the case of looking for the recombinants. So it's 34 plus 36 plus 62 plus 58, all in brackets, divided by 1,000. So what we'll do in the next step, I'll have to erase some of this to give me some more space, we'll use these recombination frequencies to assemble a map of the three loci.